everyone. Thanks so much for coming to the second Toolbox of the year. And today we have Rez Altek giving a seminar. He's the director of SEEC and also a professor here in the stats department at UCT. Rez's work focuses on conservation biology and especially in relation to climate change, and he's got an interest in the intersection of ecology and statistics. So we look forward to what you have to say today. Thanks, Rez.
Thank you, Bianca. Yeah, so I'm going to talk about estimating survival from Capture-Mark-Recapture data sets. So Capture-Mark-Recapture data can be used to estimate a lot of different things like population size, recruitment, a lot of things, but today I'm just going to focus on survival estimation only. Okay, so survival is a really important parameter for a lot of things. So if you're worried about conservation, evolution, it's a big fitness component, it's an important determinant of population dynamics. And so knowing something that survival is important in many different contexts. Now the problem is, of course, we hardly ever observe reproduction and death in nature. We observe individuals being alive and doing their thing, but we don't directly often observe when they die and why. And so what people have done for a long time is to go out, capture individuals, mark them in a way that makes them individually recognizable, and then collect data on when they are being seen again. So this could involve ringing with birds or attaching tags to animals in some way. And the problem with that is, of course, you might see the same individual again, but you might also not. And if you don't see it, you don't know what happened to that individual. Did you just overlook it, or has it actually died? So individuals disappear, but you can't be sure about what has happened to it. So what we really want to know is that state process here. So this is for full circle here for an individual that's alive, and then an empty circle when it has died. So we know it's alive when we first mark it, and then it stays alive for a while, and at some point it dies. But what we are actually seeing is the rate process here. So that's filtered by the observation process. So we catch it on the first occasion, and here, for example, we saw it again on the next occasion, then we didn't see it, we saw it again later, so we knew it was alive up to here, and then it disappears. But we don't know exactly when it has died, and the trick is now to estimate what is the probability, if you don't see it anymore, what is the probability that it has died. So, with this type of model that I'm going to talk about today, when an individual is dead, we don't see it anymore. So they just disappear. Right, so just a quick slide about the real world versus model world. So we are going to develop a model, or going to use a model to estimate survival. And obviously when we are working with models, we always make simplifying assumptions, and we've always got to check whether those assumptions are actually reasonable, and whether the conclusions that we can draw from the data based on our model, whether they are actually informing us about what's really happening out there. So we are thinking about biologists like birds or plants or whatever we want to estimate survival for. The statistician is thinking about balls of equal size that behave randomly and have all the same characteristics. So we need to make sure that the assumptions that we are making in the statistical model are actually reasonable. So here is the setup of the basic Capture-Mark-Recapture experiment. You go out at point 1, you catch a bunch of individuals. So now we obviously see the birds or the plants that we catch and mark. A statistician thinks that this is a sample of what's out there. Then we mark those individuals, we release them, and sometime later we go back and we catch another group of animals or plants, and we examine the marks and we mark unmarked ones. And so yeah, so the idea again is here that we are catching a random selection of the individuals that are out there, and so on. And now between those capture occasions, we say that there's a period over which individuals can survive or die, and what we want to estimate really are those survival rates between our capture occasions, and to do that properly, as you are going to see, we also need to be able to estimate those capture probability or recapture probabilities. Okay, so this can go on over time. The key idea is that those capture occasions are short in time compared to the survival interval. We also assume that all individuals have the same recapture and survival probability, and that marks are not lost or missed. So those are the basic sort of key assumptions. So with this experimental setup, we can then observe capture histories. So in capture history, we put the 1 if we saw a particular individual and 0 if we didn't, and each individual gets its own capture history. So for example, an individual with capture history 111 was ringed on occasion 1. We know it survived to occasion 2 because we caught it again on occasion 2, and we also caught it on occasion 3. So we also know that it survived from occasion 2 to occasion 3. And the probability in terms of capture and survival rates, the probability of observing that capture history is phi1. That's the survival probability from 1 to 2. Times P2, so that's the probability of being captured at time 2, times phi2, which is the probability of surviving from time 2 to time 3, times P3, which is the probability of being captured at point 3. Okay, so then here's another example. We've got the capture history that is 101, so the individual was marked on the first occasion, was not seen on the second, and then was recaptured on the last. And now the probability of that capture history is phi1, so we know it has survived because we caught it again later. We know it was not captured, so probability 1 minus P2. On the second occasion, we know it has survived the third, or the second interval, and it was captured again on the third occasion. So the point is we can write down the probabilities of each of these capture histories in terms of survival and recapture probabilities. Now, here's another capture history that we need to consider. Obviously, there are a lot more, but here's another interesting one. So here, this individual was marked on the first occasion, recaptured on the second, and then it disappeared. We didn't capture it on the third. So now there are two possibilities if you think about this. Either this individual has died after the second occasion, or it was not captured on the third. So those are two mutually exclusive events, and the probability of this happening is phi1 times phi2, so P2, so we know it survived, the first occasion was captured again, and then either it survived and was not captured, or it died. Right, so we can write down the probabilities for all of these, and then the likelihood of the model is just the product of these probabilities and weighted by the numbers of individuals observed in each class. And then we can use maximum likelihood or Bayesian methods to solve, to estimate these parameters. I'm not going to go into much technical details. I'm going to keep it at a very sort of technically superficial level, but if you are interested in it, there's a lot of literature behind this. So here's one key idea that I want to bring up early. When we, in the previous slide, we used a different parameter for survival between time point 1 and 2, and 2 and 3. But the way we can test hypotheses and estimate effect is that we can put constraints on these parameters. So here's an example where we are treating survival as constant. So we are saying the same survival rate applies between time 1 and time 2 and between time 2 and time 3. So by putting constraints, we can come up with a number of different models, and then we can use model selection basically to tell us which model describes the data the best. Okay, so that's an important idea. So, so if you're working with Capture-Mark-Recapture data, I really recommend having a look at the Mark book. So we are going to use Mark today in this Toolbox Seminar. Mark is the most widely used software for fitting Capture-Mark-Recapture models. There are a lot of other pieces of software and other ways of doing it. But even if you use another software, actually having a look at this book is really good because it covers not just Mark, but a lot of the statistical theory behind it too, and it's explained in a very accessible way. And it has got pointers to the primary literature. So if you're ever contemplating to work on Capture-Mark-Recapture data, I recommend having a look at the Mark book. Okay, so the first step is always data wrangling. You first have to get your data into the right format. With Capture-Mark-Recapture data, what we need are those capture histories that I showed you a bit earlier. So we are going to use a data set that Doug Hairbottle and I and some others collected on Hardydars here around Cape Town. So we started in 2006, and then for a number of years we went to Hardydar nests, marked the nestlings, and gave them a numbered coloring that people could afterwards identify and send us observations. So here, for example, it's an individual that has got code minus, it's a special one. So this one was marked in 2008 and then never seen again. Here's individual AA, it was marked in 2006, never seen again. Actually, all of these were never seen again, but we do have 261 individuals, and some of them were seen many, many times. So we've got, I think, several thousand resightings. Okay, we are going to upload an HTML file onto our website where I've got a lot more code and explanation, but also includes the data wrangling part. So if you're interested in actually reproducing these analyses that I'm showing today, it should be on our website shortly, and you can look at that document. Okay, so Mark is a standalone piece of software. It has got the graphical user interface, and it wants to input data in a particular format. So it's essentially a text file. It wants it to be called something.inp, and this row just creates the data file in the correct format from the matrix that we saw in the previous slide. So this is what the file needs to look like, capture history, and then at the end, a column that specifies that we had one individual with that particular history, and then a semicolon. So if you're new to Capture-Mark-Recapture analysis, I strongly recommend using the graphic user interface to Mark, because I find it easier to learn how Mark works. And so I quickly want to take you to that, to program Mark. Can I exit this? Like this, yeah, thanks. Okay, so program Mark looks like this. You can download it from a website screen. So I'm just quickly going to start a new project. Here you can see Mark can fit all sorts of Capture-Mark-Recapture models, actually even occupancy models. We are going to go with the live recaptures, the so-called Cormack-Trolley-Sieber models. Title, I'm just going to put in some random, and then I'm going to select the file. So that's my INP file. Quickly have a look at it. So that's what it looks like. We've got the capture history here, and then the column with ones. We need to tell Mark how many occasions we have. In this case, it's 12, was 12 years. And then you can put in a lot of other settings here that are specific to your data sets. In my case, it's all the defaults for everything else. This is just a message that I've already got a similar object. And then we are confronted with this screen here. So this is called a parameter index matrix, and I'm quickly going to go back to my slides to explain what dot is. So here is the basic setup, experimental setup again. And now, so we've got these different recapture probabilities and different survival probabilities. So now if we just look at the survival probabilities, individuals that were ringed or released marked on the first occasion, they can potentially survive all the way to the end of the study. So we've got survival rates 5, 1, 2, 3, 4, and 5 for them. So that's called a release cohort in Capture-Mark-Recapture speak. And then on the second occasion, we might release a whole bunch of new individuals that are marked for the first time then, and that's release cohort 2. So for them, obviously, we can't estimate the first survival rate because they weren't marked yet, and so we have sort of like a reduced row of parameters: 5, 2, 3, 4, and 5, and so on. So the ones that you mark on the last occasion, well, on the second last, basically, you can only observe them once more before the end of the study. Okay, so these are basically the parameters that we might be interested in for survival. And so if you just remove those signs, then you can see that we are left with this triangular matrix here, with indices 1, 2, 3, 4, 5, 2, 3, 4, 5, and so on. And that is exactly what you're seeing here. So this is dot parameter index matrix. So these are the indices for the survival parameters. And what we can do now is, so here you can see cohort 1 and cohort 2, they've got the same parameter in year 2. And so that means this particular model is going to be just time dependent. So we are going to say it doesn't matter whether we are looking at a freshly ringed, newly ringed individuals or not, they all have the same survival rate. So you could potentially change that, and you could say, well, actually, I want an age model. So let's say, for example, like this. So now all newly ringed individuals have got the same survival rate, and all older individuals have got the same survival rate. We could also potentially make them all different, and we are going to see the use of that later. So obviously that's going to give you a lot of flexibility to put constraints onto that structure, but you have a lot of underlying parameters. Or we could say it's all constant, they all have the same survival rate, and then let's just run that model here. So this would be one where phi is constant, so we call it dot, and then p, I didn't manipulate the parameter index matrix for the recapture probabilities, so those are still time dependent. And then Mark is going to fit that model, and it's going to give us some output here. The archaic information criterion, how many parameters it has estimated, and so on. Okay, so the graphical user interface is really nice because it allows you to directly see those matrices and manipulate stuff. But once you get the hang of it, it can become frustrating because, like all money-driven programs, it can be difficult to keep track of what you've actually done. And so in terms of reproducible research, you want a code-based analysis as much as possible. I mean, imagine you're doing this analysis, and then I suddenly say to you, "Oh, I've got an updated data set." No. And if you've done it the money-driven way, you have to click your way through the menu again. Whereas if you had code, you could just rerun the analysis. So fortunately, there's an interface to Mark that runs out of R. It's a true library RMark. And for the rest of this seminar, I'm going to show you how to use RMark. But keep in mind, so if you're new to this, I recommend that you spend some time with Mark as a standalone application first. Okay, so to use Unmarked, we just have to do a little bit more data wrangling here to get the data into the right format. And then once that's done, we just call the function mark. And if we call mark with just sort of with all the defaults, so the hardware, that's our data frame, but we are using all the defaults, then Unmarked is going to do something, and we get some output. And here we can see that what it's done is it fitted the constant model, so constant survival and constant recapture. So we are just only estimating two parameters, one for survival and one for recapture. You can see here number of parameters equal to 2. You get -2 log likelihoods and AIC, and then we also get those parameter estimates. So this is Mark calls these betas. Those are on the logit scale, and I should have mentioned earlier when we looked at that. Remember that diagram with the red and blue dots? So I wanted to mention there that we are actually dealing with basically binary things. So an individual can either survive or not. It can be resetted or not, or recaptured or not. And those are basically binary things. So this is very similar to a GLM with like a logistic regression. And so we are going to put constraints onto these survival and recapture parameters on the logit scale. So we are using the logit link function to do that. And so here we've got our parameter estimates on the logit scale. That's going to be more important later on. And then we also have the back transformed parameter estimate. So in this case here, yeah, it looks like, alright, what's happening? Yeah, I'm not quite sure about those rows down here, but I would have expected just to see one survival rate estimated, so it's always the same thing. And so according to this model, survival from 1 year to the next in hard loss seems to be 0.64. Now, this is probably not a good model because we ringed all these as chicks in the nest. So it's probably going to be, for example, an age effect. So this model is not very good. I want to look at a bit the more flexible model that can account for those age effects and some other effects. And so I need to, rather than just go with all the defaults, I'm going to take a little bit more control, and I'm going to do the steps one by one. So first we need to pass our data to this process.data function, and here we are able to tell Unmarked what kind of model we want to fit. So in our case, it's a Cormack-Jolly-Siebert type of model. We can also tell it what the start year or start time is. And then we pass it on to this make.design.data function, and that makes the so-called design data. So here you can see the head of the design data here, and I'm going to talk about that a little bit more, but essentially for the simpler models you don't really need to worry too much about it. But what Unmarked is doing here, it sets up sort of the data in a way that we can fit time-dependent model, cohort model, age-dependent model, and a few other things. So yeah, so I think I'm going to not. Oh, yeah. So what it's actually doing in the background, Unmarked is going to tell Mark it wants those parameter index matrix set to all different. So every parameter has got a different index, and then based on a very flexible underlying model, we are going to put constraints. So we are going to say, for example, if we want a time-dependent model, we are going to say parameters 2 and 6 should be the same, parameters 3, 7, and 10 should be the same, and so on. So we are going to constrain it to make it, for example, time-dependent or age-dependent or whatever we want. So we are modeling variation in these survival rates on the logit scale using the generalized linear model types of ideas that I'm hoping you're all a bit familiar with. Now the xi here, these are covariates. Most often we look at time, so we can say time survival differs from one year to the next. Age is an important one if you've got individuals of different, of different age, as you always do. And then sex, often maybe males and females are different. In Hardidars, we didn't have sex for many of them, so I'm not going to look at that. But then other types of covariates are environmental covariates, like rainfall. We might have a hypothesis that survival depends on rain or temperature or whatever. And then we can also have individual level covariates. So for example, size of fletching. So those are covariates that are unique to an individual, but stay constant for that individual through time. So you could also have time varying individual covariates, but the difficulty is if you don't catch an individual, you don't know what the value is of that covariate. So those are a little bit harder to deal with. So I'm not going to, so that's a little bit more advanced. Then the betas here are those are the parameters we want to estimate. Okay, so just back to that design data object. So this is actually mapping those x onto the all different parameter index matrix. So we see, for example, this is not exactly the matrix for the Hardidars because we have 12 occasions. But like, for example, here, parameters 1, 2, 3, 4, 5, they are all part of the first cohort. 6, 7, 8, 9 are the second cohort, and we see parameter 1 is time 1, 2 and 6 are time 2, and so on. And so we are mapping those. So parameter 1 is the cohort that was ranked in 2006. They were all age 0. Time was 2006, and so on. So Mark is setting up that mapping between the types of variables that we are interested in and those parameter indices. Okay, so for the moment we don't really need to worry about this more. We just know Mark is doing that in the background. Now we can use those variables to set up models. And so I'm doing it in 2 steps. I first generate a collection of model structures. So dot is for the constant model. So this is everyone has got the same survival or recapture probability. Time stands for the one where I'm going to allow survival to be different between the years, but nothing else. Age, so that means they differ between first year birth, second year, third year, and so on, but not over time, so it's just age. And then we've got a model structure here that allows survival or recapture to vary between the years and with age in an additive way. So that means we don't have an interaction. So that means in a year where say the chicks survive poorly, the adults are also going to survive poorly. So that's kind of the model idea here. And then we call that function mark again. And now we need to give it the data and the design data. And then we need to specify the model structure. So I'm going to say I want survival to be time dependent and recapture probability to be time dependent. And then I can fit that, so I can get the summary output. So it's fitted the model phi time, p time. And then now Mark thinks we have estimated 22 parameters. So we have 12 occasions, so that means 11 survival rates potentially and 11 recapture probabilities. And that's where the 22 is coming from. You can see here it says unadjusted equals 21. We're going to get to that in a moment. Gives us the maximized log likelihood and AIC, and then parameter estimate. So this goes on for a while here below the screen. So now, if we look at those estimated survival and recapture probabilities. So we get an estimate for the first year here, 74%, second year 35%, third year 81%, and then the last year it's 72%. But now this here should raise a red flag. So the standard error for this estimate is 0. Obviously that can't be true, right? We are not completely certain. We can't be completely certain what R should be. And if you look at the recapture probabilities here, you can see also for the last recapture probability we have a standard error of 0. So this flags a problem. Now it turns out that the information on the recapture probability, as you can imagine, comes from those internal zeros. So if I mark an individual, I don't see it, and then I see it again later, I know that individual has been alive, and that tells me that I didn't catch it, so that tells me something about the recapture probability. On the last time step, I don't have any further data to tell me whether what I'm seeing right at the end, whether that's due to lower survival, for example, or lower recapture probability. So that last, in the fully time-dependent model, that last survival and recapture probabilities are confounded. So the model basically can only estimate the product of those two. And so that means we actually only have 21 parameters because those last two probabilities are confounded. So to summarize that, so Mark tries to work out how many parameters were actually estimated, and it has some clever ways of doing it, but it's not completely foolproof. Like, for example, sometimes you might not have enough data to estimate a particular parameter, and Mark then says, well, I wasn't able to estimate it. But if you're thinking about model complexity, you should probably count that parameter because you might be fitting a really complex model, and you want to make sure that model complexity is taken into account when you do model selection. So Unmarked takes a different approach, and it assumes that all the parameters that you have specified are estimable. And the upshot is that you've got to look at these two, and you've got to double check that they are correct. So even if they agree, they might both be wrong. So you do have to do a little bit of checking and adjust if necessary. So in this case here, Mark was correct, and we have to adjust the parameter count to 21. So that's what I'm doing here. Okay. Now, right. So then I can fit a whole bunch of more models here. So I'm going to go a little bit quickly here. And then I can, after I fitted a whole bunch of models, I can then look at which model is actually describing my data the best. And Unmarked has got a simple function here, collect.models, and that creates the model selection table. You can see here in our case now, the model that allowed survival to vary over time and age was the best one. It had the lowest AIC, and the others were all quite a bit worse. Right. Now here I'm plotting the estimated survival probabilities, and you can see here, so the black line is these are the birds that we ranked in 2006. The red line are the birds that we ranked in 2007, and because we have an age and a time effect, they vary sort of in a similar way, but slightly offset. And what worries me about this plot here is that a lot of survival rates are estimated at 1 or 0. So that to me is an indication that we are trying to estimate too many parameters. So even our best model here is over-parameterized. If you think about it, it probably makes no sense to assume that, for example, a 6-year-old bird has got a different survival rate from a 7-year-old, 8-year-old bird. So we want to be a little bit more sophisticated about the age effect. And so here now we need to actually take that design data again, and we need to manipulate that design data. So what we do is we are going to add a column that just distinguishes between what I call juveniles. So these are 0 to 1-year-old, immature for the one from 1 to 2-year-olds, and then older than 1, I call adult. I'm going to add that to this design data, so you can see now I've got an extra column here. So these birds were ringed in 2006, they were juveniles. In 2007 they were immature, and then they became adult, and they stay adult for the rest of their life. And then this is the next cohort here, the birds ringed in 2007, they were juveniles then, immature in 2008, and then became adults. So the point I want to make here is not just I'm illustrating it with an age effect, but you can potentially manipulate those top design data in whatever way you want, and then fit models that have that kind of structure. Okay, so I called it age class, and I'm going to fit 2 models with age class here. So this is just age and then time plus age. And when I do the model selection table again, I can see that now the model with time and age class came out the best. So we've got a bit of simpler model, down from 22 parameters to 14, and it looks like it's a better model according to AIC. And here you can see the survival rates for the first cohort. So these are the fledglings, immature, and then they become adults. And obviously, over time, fewer of these individuals are alive. So and also we put in most effort early on in the study. So those survival rates have become a little bit imprecise, and that's just a reflection of us not having a lot of data there. But it looks like adults are surviving between about 80 and 90%, which seems reasonable. Okay, so now we need to ask ourselves, are any of these models any good? So remember that real world versus model world type of thing. And I mentioned the key assumptions. So every marked individual has got the same probability of recapture. Every marked individual has got the same probability of surviving. Marks are not lost or missed, and all samples are instantaneous. So it turns out this last assumption here is not so important. So if in our case, we were reciting those hardy data over quite a long time, and there's been some research saying that this type of violation isn't that important. If you lose or miss marks, then that's important. For example, a lost mark means so we are actually following the marks, not the individuals. So that means if a mark gets lost, then not that's going to lead to survival estimates that are biased low because the tag has essentially died. Okay, so we can, so these 2 first assumptions are important, and we can test them using quite classical goodness of fit tests. I'm running a little bit out of time, so I don't want to go into too much detail, but basically those goodness of fit tests are based on contingency tables, and those are classical tests called test 2 and test 3. Test 2 has got to do with equal recapture probabilities, roughly, and test 3 has got to do with equal survival probabilities. So I'm just going to show you how to do that in R. So the classical software is called Release, and then it was implemented in a software package called UCare. And since, like, for the last few years, there's been an R package that does exactly the same as the standalone software UCare. It's called R2UCare. So it needs the data in a slightly different format again. So this is a little bit of data wrangling here, those 2 lines. And then I'm going to use that function overall underscore CJS, and that does the overall goodness of fit test, including test 2 and test 3 that I showed you on the previous slides. So we do that. So the null hypothesis that we test is that the data follow the hypothesized pattern. So we have so these are like coin flips. We've got no extra variability. The data follow a multinomial distribution with known probabilities, and what we are testing here is deviation from that null hypothesis. So a small p-value, the large chi-squared value, means we have strong evidence against the null hypothesis, and so that's something we need to worry about. So here, these data are very strongly, so this indicates that our data very strongly violate our underlying assumptions. Okay, so this is an overall goodness of fit test, but we can now drill down into the individual components of this test. So on the left-hand side are two different versions of the test 3. So this roughly has got to do with survival. And maybe as a first step, we look at those p-values here. And you can see those p-values are not terribly small. If you look at the test 2, here's where the really small p-value comes in. So that indicates probably that we've got an issue with the assumption of equal recapture probabilities. And in fact, what happened with the Hardy-DOS is that we ringed them over quite a large area, all over Cape Town, out to Paarl and Stellenbosch, but the reciting effort was concentrated in Constantia. So there's a very strong spatial variability in the reciting probability, and I think that's probably what's drawing the problem here. So this model actually doesn't fit very well. I wouldn't rely on it as it is, and I would have to try to sort of model out those spatial patterns a bit better. Okay, so still about the goodness of fit test. When you get an indication of your assumptions are violated, you need to find out why and how you can improve the model to fit your data better. And so looking at the raw data is always a good idea. You always need to make sure that your model makes sense given what you see in the raw data. Now, Capture-Mark-Recapture data are a little bit difficult to visualize, but one suitable way is the so-called M-array. So here we've got the vector of the number of individuals that were released on a particular occasion, and then this matrix here shows how many of these individuals were seen again for the first time in the following year, and then every subsequent year up to the end. So this means in 2006 we ringed 27 Hardy-DOS. 8 of those were seen again in 2007. 1 was not seen until 2009. 2 were not seen until 2010. And 16 were never seen again. So what you want to see here is the highest number down the diagonal. So it's reasonable to assume that the very next year you're going to see most of your ringed birds again, and then fewer as you go over like this. This sort of seems to indicate that that's okay, but it's also going to flag sparse years. So you can see here in the later years we ringed very many fewer birds than in the earlier ones, and that's why we saw those problems with the survival estimates in the later years. Okay. Am I out of time?
No,
okay. Okay, so finally, there's this issue of over-dispersion. So if our data nicely work like billiard balls or like coin flips, then we should, then the variance is given by the binomial distribution. But because these are real birds, real organisms, they work differently. They are not independent of each other, perhaps. They vary in their survival and recapture probability, and that causes over-dispersion. So that causes more variability than what we would expect if these were all just coins. And so actually the problem is also, or one other view of the problem is to estimate how big that over-dispersion is. And one way to do that is to extract the chi-squared value from the overall test and then divide it by the degrees of freedom. So this gives us an estimate of the over-dispersion. And if there's no over-dispersion, then that should be close to 1. If that's very large, then we know there's a problem. So 2.7 is not, it is a little bit worryingly high, but it's not super high. And so if you've tried everything, you can't really come up with a better model, and that over-dispersion factor is not too high, you can adjust your model selection and your confidence intervals with that over-dispersion factor. So what that essentially going to do is it's going to inflate your confidence intervals to account for the over-dispersion, and it's going to tend to make model selection favor simpler, relatively simpler models. Okay, so just to wrap up on the goodness of fit test. So if test 2 is significant, then that might be a trap response. So in our case, I've got to point it out that we had an indication of individuals that were seen in 1 year were more likely to be seen again in the next year, and so on. And the reason for that is that just some individuals are always more likely to be seen. So if you see them this year, you can say, I'm probably going to be seeing it again next year. So that's a trap response. You will sometimes get the opposite if individuals learn to avoid your traps. And then there might be temporary emigration. So individuals, like for example with the albatross data, Kim is working, for example, these individuals disappear, they breed, and then they disappear because they only breed again 2 years later. So that's temporary emigration, like in a 2-year cycle. And you can use multi-state models to account for that. If test 3 is significant, so that means there's probably a problem with the survival part of the model. You can look at age effects. You can maybe check whether the cohorts differ. Transients, so these are individuals that you happen to capture because they came through your study area, but then they disappeared. And there are ways of dealing with that. And then, as I said on the previous slide, you can apply an over-dispersion factor if you really can't find a better model. Okay, that brings me to the end of my seminar. I wanted to point